Hello, my name is John Metzcar. Today I'll be presenting a setup guide or an install guide for PhysiCell for the macOS operating system. I am a PhD student in the Math Cancer Lab, and I'm happy to present this material today for the upcoming PhysiCell Hackathon, the 2023 Hackathon, as well as into the future for as future-proof as we can make this. So let's get started. All of our training material for the upcoming 2023 Hackathon, as well as just general updated training material, is going to be located at this website. You can also follow this QR code to find it. And these slides themselves are located in this website as well. This presentation was written by Randy Heiland and myself, and I'm happy to present it on the team's behalf. So in terms of what we're going to go over today, we're going to go over multiple installations for the pieces to create basically a PhysiCell ecosystem. The core part of the presentation is about getting the compile chain available and then showing that it works. And so we will be doing, that's the first step, is getting compiler. Then we'll get our source code for PhysiCell, make it, and then show that it executes. From there, we'll basically go into some Python stuff. First, we will obtain the correct version of a proper version of Python, then test that by building a different sample project. ImageMagick will make ImageMagick available, which is helpful for image manipulation, for ImageMagick, if you will. And then finally, we'll cover getting the PhysiCell Studio, which is vital for creating and editing PhysiCell models and dependent on Python. Then we'll look at some additional items that will either be part of the hackathon and or are just a good idea to have around. But before we get started, there's a couple notes about this install guide itself. We've tried to make all the terminal commands boldface, and so that they stand out, as well as making them able to be directly selected and copied via Command C and pasted Command V directly into the terminal. We also assume that you have an open terminal that you can access for the purposes of installation and execution. Note that this is a static document, so it's possible the commands could vary slightly as version numbers change, and I'll illustrate that as we go along. In fact, I have a good example of that already in this document as these codes are evolving. And then finally, of note, there are some slight differences between the older Apple chipset and Intel CPU versus the Silicon, the M1 or M2 CPU, which is an ARM-based system. So if you have problems, let us know. We'll do our best to help you out. Let's get started with getting that compiler. So briefly, your computer came with a compiler, a C compiler. It came with a Clang compiler, and that compiler is not OpenMP enabled, which means it can't take advantage of important aspects of the way PhysiCell runs, the parallelism that's available in PhysiCell. So we need to install one that is OpenMP enabled. We're going to be doing that through Homebrew, which is the package manager for macOS. To get Homebrew, you can follow this link. Visit the web page. We want to install Homebrew. This is a shell command that will run in a second, or that you will run in a second. To copy that into your buffer, they've conveniently got this button there. Now navigate to an open terminal, and that command is already in your buffer. So Command V will enter it into the terminal, and then you simply hit enter and it will run. In my case, I already have Homebrew, so I'm not going to run it this time. You can find out more information about Homebrew and kind of their install guide right here. Like I said, hit return to execute the command, and then basically hit return until it's done. When the installation is finished, you should be able to verify that you have it by entering this command into the terminal. Should return something similar to this. It's outlined in our install guide. So again, slight difference between the Intel chipset and the Silicon chipset. Once you've installed Homebrew, now we can use it. That's the important part, right? We are going to use Homebrew to get the GCC compiler that's distributed through Homebrew. It's a new compiler, GNU new. So we'll grab this command, brew install GCC. This is saying invoking brew. This is telling it to install this package. So Command C, Command V, enter. That might take a few minutes. Basically, you just let it run. You can look here to find which version you've installed. In this case right now, it's installing version 13 point something. When it completes, you can use which to see where it was installed and basically verify that it was installed. So Command C, Command V. In my case, it returns nothing because I actually have 11 installed. So I'm going to alter that to 11. This is an example of where our version numbers have changed over time because Homebrew is now distributing GCC 13. I have not upgraded apparently. And then here I've confirmed that I indeed do have this binary. Note that if you use this install guide later, say much after July 2023, this is an example of a command that might need updated. So because at some point Homebrew will switch to GCC 14 as things change, just like anything else. There are other similar points later in the presentation, and pretty much anytime there's a version number, it may change. So that's something to be aware of, especially if you use this later. Now, we're gonna have one more thing we need to do. So we have our, we've gotten our compiler basically by getting a package manager. Now that we have that compiler, we need to set an environment variable, and that environment variable will tell our makefile, which will be included in the PhysiCell download that we'll get in a minute, where to look, what compiler to invoke. There is more information or similar information available in our quick start guide, but that's been deprecated. So it may or may not be helpful depending on when you access it. For now, I think it's probably a good resource. And hopefully this video is helpful as well. So to define an environment variable, this is basically what you do. Export, this is the variable name, and we're going to set it equal to this string. So we can copy paste. However, that's only for this instance of the shell, for this particular shell that I have up right there. So to really use it consistently, you're going to want to make it so that your shell always loads and always initializes this variable and sets it to this string. In order to do that, you'll need to set up a bash profile file or a Z shell environment file. My computer is running bash as the default shell. You can see that here. Return bash. Newer Macs, the Macs now default to Z shell. So if you run this command in your terminal, you'll find out if you're running bash or if you're running Z shell. If you're running bash, you need a bash profile file. For Z shell, you need a Z shell environment file. And you want that placed in your home directory. So from wherever you are, which you might be at home right now, if you do cd tilde, you'll go to home. And then from there, you can do touch bash profile. And the command touch will create a file called bash profile. Or if you're running Z shell, then you would do touch.z shell. You can copy and paste it straight from here. Oops. Let's ignore that for now. Sorry about that. Now, so the order is change to your home directory. That's cd tilde. Then create a bash profile or Z shell environment file if you don't have one already. And then finally, when you do have it, you'll need to run this command. Again, depending on if you're running bash or C shell. Get out of that. And this command tells, basically it puts the line that we did up here into this text file, and then this text file loads every time you start a new terminal. Great. In order to test that, you can start a new terminal shell, and when you start a new one, you could hit, for example, Command N. It will cause your new variable name to be initialized and set to our G++-13. And so then when you execute the command echo this variable name, in this case, the $sign indicates that it's a shell variable. So echo send to terminal. This variable name. You'll see that I accidentally put it in my case, G++13. That's because I didn't, let's see, this terminal won't do that. It'll do this. Great, 11. And in this case, it's the reason it's reading 13 is because I executed this command up here, but it's not actually permanently in my system. Anyway. Great, so you should see the appropriate variable echoed back out. So I kind of got into this already. This instruction is highlighted and it appears several times. We really mean it. When you start that new terminal, that causes multiple programs to launch or relaunch. And in this case, it will source or initialize your bash profile or C shell environment file. Great. So now hopefully you have homebrew if you didn't before, which will be useful. It's useful in general. We'll use it later actually. And the new compiler from homebrew, and that you've set your environment variable PhysiCell_CPP to the appropriate string. Assuming you've done all that, you'll be ready to compile PhysiCell. First, though, we need to get the code. So let's get the code. To test building or running a PhysiCell model, first we have to get the code. So open a browser and navigate to this link, or just this link in your PDF. This is a Python script that should run on anyone's Python, even if you haven't installed Python, a newer version of Python. I'm going to name that file get PhysiCell.py. Perfect. Now it's there, and I can use it. Oops, sorry about that. Let's get like this. Perfect. And what it's going to do is it's going to get the latest PhysiCell release, is what that Python shell does, or Python script does. Here are the commands to do it. This is obvious. This is assuming that you've put it in downloads. So I already have downloads on my terminal or prompt set to downloads. So I'm going to execute Python. This great, and it's echoed out that I got this particular release. Now I'm going to move it to my home directory. You can move it to wherever you think is appropriate. I actually keep all my PhysiCell stuff in a directory called GitHub, because I use GitHub. But for demonstration purposes, I'm going to move it to home. That's what the tilde will take it to home. So move mv this file name to home. Now I need to change my prompt to home. So cd change directory tilde go to home. You can also do this manually through the GUI file explorer system. And that has unzipped my zip file. And then that means that I should be able to put my prompt in that directory. Great. So now I'm in the PhysiCell directory of my fresh copy of PhysiCell. And this is what, if you type ls, it will list the files that are in the system. This is what I would expect. Folders of source code, as well as additional items. Now I can type make. I've found that you actually can't do this, at least at this stage. Later you can type make. Nope. So if you add this extra command, I shouldn't have put that space there, you can get it to compile a little bit faster because it'll multi-thread the compilation. In this case, it's going to go a little bit slower. So what's happening right now is our make file, which you can see it named here. Our make file is invoking the compiler, in my case, G++11 from Homebrew, to compile multiple sets of binaries, multiple binaries from our source code. And it's just basically going through every single file as specified in the make file to get our code. This first one will take a little bit longer. Great, I paused that for just a second. Not too long. And our make file is complete, and it lovely gives us the name of our executable that we just compiled, heterogeneity. So you can see that here. Our output on my terminal is similar to what's in the PDF. Now we can run the model, and it should execute without error. And this will basically, I'm going to clear the screen. Clear will, now my prompt's up at the top. I hit return, and I enter in the command, hit return, and it's beginning. Great. Now I can see that it's done one simulation step. So simulated now 180 minutes, 240 minutes, and I'm going to hit Control-C and stop the simulation. This is enough to show that it's working. And at the top, you PhysiCell, when it executes and it initializes and then begins to execute, it gives you a lot of information. But what you can see here is information that can kind of verify that you run the correct simulation, the simulation as you intended to run it, as well as if it was appropriate, you could put this into a record. So what we're seeing here is it's running this particular settings file. There are these parameters, global parameters available. Here's where this is indicating the boundary conditions. And then now we get into the microenvironment and what substrates are there. For example, then we have a listing of the signals that are available to cell agents to update, as well as the behaviors that can be updated with those signals. Then finally, we get into the cells themselves, the different cell definitions that are available in this particular simulation. In this case, we have one type, and it's named cancer cell. And this specifies its default phenotype, basically. And then this particular output is specific to this model. Great. Now, continuing to follow the guide, we're going to confirm that we got some output. Just in case, we're going to solve that PhysiCell was doing its thing based on this. So we've got output happening. Let's do ls. Actually, let's clear ls output. Our output by default goes to a folder called output. Great. Now I see multiple PhysiCell outputs, including some initial information, the initial setup, and then the time steps. Furthermore, we can look at an SVG and show that we have sort of the expected output. So I use the terminal for that. I'm going to do open output SVG. Great, and I'm going to do 1. There it is in our browser. Great, not the same. There's some stochasticity in these simulations, but similar. Great. So with that, you should have everything you need to make and run a PhysiCell executable, and hopefully it executed without error for you, producing results similar to what you just saw on the video. Now we're going to get into Python, a Python section, and sort of like I'd say other things that are very close to the core of the PhysiCell ecosystem, especially the PhysiCell Studio. But first, we have to make sure you have the right Python. So we need Python 3, and this is a note saying why we need Python, justifying it. I think that it's overall just very useful, and we use it. I know I use it throughout my PhysiCell work. We're going to want Python 3. Your computer may have Python, but if it's Python 2, everything that we're going to be discussing in the hackathon and in general, the PhysiCell ecosystem that's made in Python uses Python 3. You can, as you've already seen demonstrated, you can use the command which to find out where Python is on your computer. And then if you type Python, it'll start a Python prompt. And but before it starts the prompt, it'll print out information on what Python it's actually invoking. And all that said, not only do we want Python 3, but we really want some particular modules that are going to come that work with Python 3, like NumPy, for example, for our analysis. And that's where Anaconda comes in. Anaconda is a bundled distribution of Python with many, many other packages, such as NumPy, SciPy. And they're not part of the standard library, but they're very useful. And it works well together. That's why we recommend it. So if you navigate to this webpage, you'll probably auto find what computer you're at, and then you can download the appropriate binary for Mac, either an Intel or an M1 or M2. And it'll just download its own. There it goes. And then Anaconda, of course, has its own install guide that you're welcome to follow. We're going to sort of very briefly go over what it looks like. Finally, I'll note that if you, I suspect that if you wanted to, a Anaconda installation would work, although that's not supported, fully supported in our, certainly not in this install guide. But if you may find that works for you too, if you don't want to download the full Anaconda package. So what you'll get is package, it's typical installer. In my case, it's for x86-64 because I have an Intel chipset. And so you can either double click this and it will start to execute, and the setup wizard will appear. It'll look similar to these, like the screenshot. Basically, you want to follow it, you want to do it. If you're using the command line, you can type in the command from downloads or wherever the file is located, type open and then the name of the file, and that will also begin the setup wizard. There's a full there's a full command line installation if you want it, and that's available here. We're not going to go over that today, though, in this video. So basically, you just hit continue until it's done. You'll want to install it for a single user, and that's what's recommended in the wizard. And it'll take a little bit of time. Then, once you've done all that, you can confirm, you can re-execute those commands that you may have executed on the slide before, where you're going to look at what Python you're using. Okay. And I'm using Anaconda. This is because that's what we recommend. And then I have Python from Anaconda. Great. So now you have Python, the appropriate Python. And we can verify that by building an intracellular model. In this case, we're going to build a sample project that uses that's based on ordinary differential equations for updating a cell state. This will also introduce you to some of the make commands that are very useful. So if we execute command make reset here, we'll set our PhysiCell back to how it was when it shipped, except for there are still some compiled binaries. This gives us access to more sample projects. So you can find out what sample projects are available by entering this make command. And in our case, we're going to want this one. So I'm continuing to follow the guide. I'll flip back to it in a second. You make ODE energy sample. And now it's brought up everything that's required to make ODE energy sample. And then we'll type make, and it'll begin to make this. And in particular, in this case, we need to download a large file, a relatively large file. So I'm going to pause the recording while mine downloads. And this is downloading the solver for the ODEs. It's a library, C++ library called the Bronar. Great. So we just finished the download of the solver. If you are going to use PhysiBoSS, which uses MABOSS, a Boolean network simulator, there's a similar process to download that solver. And I believe the same is true for the FBA example. So now we've created our, it echoes back out to the terminal. The makefile does that. We've created this sample project, and then we will run it. Note though that we will get an error because an environment variable isn't set. Yeah. Oh, we didn't get the error because I've already played around with it. All right, so let's do one thing at a time. If you haven't set an environment variable yet, you will get an error. And in order to fix that error, you set this environment variable. Similar to setting the PhysiCell compile command, and it should execute without error. And if you want to permanently fix this error, if you're going to be using this a lot, then you'd want to add this to your your .bash profile or Z shell environment file. Now, the other thing that happened is that we did get an error, and this is a known bug. I didn't let it run quite long enough, but you may have seen that. It is a known bug. So if you see that error, don't worry about it. We're working on it. But for the purposes of this installation guide, this doesn't matter. This is just a demo. Great. This is explaining how to export your the path to your bash profile or C shell environment file. Great. So now we have Python. We've demonstrated its use in the ODE setup model. And now we're going to get ImageMagick. ImageMagick, this is pretty straightforward. It's an image manipulation command line tool. You can learn more about it by going to this website. To get it, we recommend using Homebrew. So brew invokes brew, install this package. So copy paste this into your an active terminal window, and it'll get ImageMagick for you. The magic of the package manager. Then you can verify that installation by what is perhaps now familiar. We find program. In this case, convert is an alias for ImageMagick. And so convert is a program that comes with ImageMagick. So now we can see that convert is in our other binaries. Our previous quick start guide does have some interesting ImageMagick commands and kind of documents what's available in the make files, so that there's some make commands that you can use to do some rudimentary image manipulation or make a GIF. Also shown here are some commands that could be useful. For example, this command will convert a series of SVGs into a GIF. And then now we get to the PhysiCell Studio. This is really important. This is for the hackathon, and as well as just for maintaining, altering PhysiCell models. So PhysiCell Studio is a GUI, graphical user interface, that lets you create and edit XML. And those XML files define almost everything in a PhysiCell model at this point in PhysiCell's development. It also really helpfully lets you run a simulation. You can plot results and more. So it's very helpful for troubleshooting, very helpful for development. You can get the latest release here. You simply click on this. It'll download automatically. And then you need to copy or move the .zip file to the same level as wherever you're using PhysiCell. In my case, like I said, I may have already mentioned, I usually use PhysiCell and a GitHub, a directory called GitHub. So I have a copy of PhysiCell Studio there, and then I can very easily invoke it whenever I have need. So in this case, we'll take the zip. We're going to move it to home. We can unzip it, and already I can tell you this is not the current version number, because Randy is constantly working on it and making it better. Here's my home. If I wasn't in home, I could do this, and I'd be in home. Now we're gonna, but it's not gonna find it. So I need to change my command. Great. Now I've got it. And likewise, this command will need changed. If you're going to use this a lot, I'd change the file name. I mean, I'd change this to something like maybe PhysiCell Studio. Or you could also, if you're feeling fancy, create an alias for this. Anyway, this invokes Python, and I'm telling it to look in home. This way, even if I'm not in, so I'm giving it an absolute path. Even if I'm not in home, this will find it because I'm using that tilde. Now it's starting the studio. I get this error. That's because I didn't give it a particular XML file to look at. So instead, it tells me that's loading the default. And here we go. And I know you'll get much more familiar with this in the upcoming hackathon. And I know Randy's doing a tutorial on this as well. I'll just close out of that. Great. So if you've gotten this far, your Python should be working. Your compiler's working. You've got almost all the tools you need. There's one more tool we're going to load up that's sort of directly in the PhysiCell ecosystem. That's the PC data loader. You can find out more information. So this is a Python-based data loader, facilitates post-simulation analysis. You can find out more information, tutorials, how-tos on the tool's website. And then instead of downloading the source, in this case, we're using pip, which is a protocol for getting Python files, Python programs. So pip3 install PC data loader, PCDL. And it goes through the requirements, and then boom, you're done. And you can use it. PC data loader should be now be available for import in any Python prompt. I believe you do import PCDL. And you can always refer back to the documentation there just to confirm that. All right, almost done. So the last thing, the last sort of program you need to grab is an SBML editor. This will be demoed and used during the hackathon. So SBML, Copasi is the one we're going to use in the hackathon. It's one of several SBML editors. So first, what's SBML? SBML is a language that's used to encode biological models, often intracellular models. So the ODE sample model is written in SBML, as well as the FBA model. Stands for Systems Biology Markup Language. So it's like PhysiCell XML, except it's specific, it's more general and used in all kinds of different models. But it's basically XML. And then Copasi itself also acts as a simulator, so you can simulate some categories of mathematical models, such as ordinary and stochastic differential equations, among other features. And it's a graphical interface for editing SBML, just like PhysiCell Studio is a graphical interface for editing, if you will, PhysiCell XML. Of course, you can get other SBML editors, but in this case, we're using Copasi. So to get Copasi, you would navigate to their downloads, similar to what we did already with Anaconda. You get the correct binary for you. In my case, I believe I would get this one, but just depends on what you have. They, of course, have their own support and installation guide for Copasi, and if you're welcome to, I recommend looking into that to make sure that you're doing it correctly if you have any trouble, but it should run smoothly. And the only hiccup could be that it triggers Apple's security warnings. So because it's not from the App Store. So when you go to execute the installer, it's a DMG. When you go to execute the DMG, you may get this warning. And so you need to go to Settings, Security and Privacy, and then the General tab in Security and Privacy and say Open Anyway. And then it should be fine to accept the defaults. Great. Now we're down to a couple things that are more sort of general code-based. When you get to the point of editing custom C++, so there may be some things you can't do, your questions in XML. You may have some rules that need explored or questions that need explored that you need a little bit more nuance or control over than what you can get out of the XML. And so you might want a decent code editor to do that. So if you're already using one, great, keep using it. And if you're new to programming, basically, we suggest as getting started Visual Studio Code. It's an integrated development environment that's free and works. It has Git integrations and some other nice features. You can also use it to edit Python. And there are many editors available, anything from just simple text-based editing like Vim or Emacs to specialty editors like CLion, which is developed by JetBrains, and it's only for C. They also have a specialty Python editor called Python. But this is a great general one to get started. That's what I use currently. Similarly to the code editor, we recommend that you use version control. You'll be seeing that in a hackathon, and you'll see that all of our materials, all of our training materials, and the source code is available on GitHub. So it uses get, which is a system of version control, and that helps prevent mistakes. It helps know when you've made changes. There's a great graphical user interface for GitHub that you can download, or you can use command line. Bottom line is, if you're editing code, it's common to use version control for the code and to enable sharing with collaborators. So if you're already using version control, great, keep using it. If you're new to programming, we recommend using get. And you may even already have it, and you could access it through Homebrew. A lot of different ways to get. And then in addition to get, there's this website called github.com, and it's a great place for sharing code and comes with a lot of features, including a graphical user interface, if you want to use it. And then finally, we encourage you to, I hope this video has been helpful. And even with helpful videos, sometimes we still run into problems, either with running or installing, or maybe you just have a question. So we encourage you to join it and actively engage with the community at our Slack workspace. And you can post questions and hopefully share some successful modeling stories. You can also submit tickets to SourceForge. And of course, please follow the project as well as the project lead, Paul, on Twitter. And I'd like to thank, this is our funding acknowledgements page. So I hope this, as I said already, I hope this has been helpful. And if you need help, just reach out. Thanks.